With this video, we're going to go over a weak acid and strong base titration. So a few things to think about conceptually before we get into the calculations is that when you look at a graph of a weak acid strong base titration curve, you're going to notice that the initial pH is higher than if we had a strong acid strong base curve. And we also get what's called the buffer zone. So this is where the resistance to that change in pH after the addition of that strong base is happening. And so we're going to look at the calculations in that specific zone. That's where we'll be looking at Henderson-Hasselbalch. You'll notice that the change at the equivalence point is also going to be more subtle. So you'll notice that with calculations. And then we'll also take a look at calculations that are happening after we've reached that equivalence point, which will be higher than a pH of 7 because we're adding the strong base to the weak acid. And so we'll look at those excess base calculations as well. This is an example of a weak acid strong base titration problem. We're going to take 25 milliliters of 0.1 molar propanoic acid, and we're going to titrate that with a sodium hydroxide solution that is also 0.1 molar. So if you envision this, you would have your sodium hydroxide in the burette, and then you would be adding that to the 25 mils of acid in the flask. Now, since we have not added any base yet, this is just at the very beginning, we're looking at that propanoic acid. We know that concentration is 0.1. And so we can just set up an ice table using the equilibrium expression to calculate the H plus and then the pH. And so that's what you see happening here. We know that we have x squared on the top for the H plus and the C3H5O2 minus. You can use the 5% rule to calculate that value of x using that 1.3 times 10 to the minus 5. That's the Ka, which they gave you in the beginning of the problem. You solve for x, and then again take the negative log of that to get the pH. So that x is going to be equal to your H plus concentration. So our pH is 2.96. If you take a look at the titration curve, so thinking about this graphically, you are at the very beginning, 0 sodium hydroxide has been added. And so this would be the same type of calculation that we were doing for chapter 13 and chapter 14. For this next part of the problem, we're going to calculate the pH after we've added 8 milliliters of sodium hydroxide. So we're going to figure out our millimoles of sodium hydroxide that was added. So 8 times the concentration, 0.1, that's 0.8 millimoles. So I'm doing this millimoles calculation so I don't have to change the milliliters. So I have 0.8 millimoles of base. 25 mils of acid is what we started with. That concentration was 0.1. So we're beginning with 2.5 millimoles of acid. And so our next step is to figure out what these concentrations are. We need to take the 2.5 millimoles of acid and subtract the 0.8 millimoles of base. This will tell us how much acid we have left because we have neutralized the 0.8 millimoles. We also need to know our total volume in order to figure out those concentrations. So we have 25 milliliters plus 8 milliliters. That's going to be 33 milliliters total that we have in the flask after that addition of base. So to calculate our concentrations for the acid, we're going to take 1.7 millimoles divided by 33. So we have 0.0515 of the acid. And then we're going to take the 0.8 millimoles of base and divide that by the total volume, also 33 mils, and that will give us our concentration, 0.0242 of base. So we've now entered on the graph the buffer zone, and so we can use the Henderson-Hasselbalch equation here, where our pH equals the pKa plus the log of the base concentration over the acid concentration. To calculate that, we're going to take the negative log of the Ka, which they gave us at the beginning of the problem, 1.3 times 10 to the minus 5, plus the log of the base concentration that we just calculated, 0.0242, over our acid concentration, 0.0515. We're going to plug that all in, and then we're going to get our pH value, which is equal to 4.56. So our pH has gone up a little bit because we have now added sodium hydroxide to that initial 25 milliliters of the propanoic acid. So moving right along, we're going to take a look at the calculations once we add 12.5 milliliters of the sodium hydroxide. So to calculate our millimoles, we take the new volume times our concentration. We get 1.25 millimoles of the base. We're going to subtract that from the amount of acid that we started with. So again, that's the 2.5 millimoles of acid. When we subtract these, the key thing to notice here is that we have used, or we've neutralized exactly half of the acid that we started with. And so this is a key point on the titration graph, and that is called the half equivalence point. So when we have neutralized half of the acid that we have started with the base, that's called the half equivalence point. And at this point, the pH is equal to the pKa. And so they gave us the Ka at the beginning of the problem. So math-wise, what we need to do here is take the negative log of that Ka, 1.3 times 10 to the minus 5. That will give us the pH at this point on the titration. So again, just to reiterate here, on your titration curve, we have the half equivalence point, which is where we are now, that is halfway to the equivalence point that would be on that straighter part of the titration curve graph. Next, we're going to take a look at the addition of 24.5 milliliters of the base. So we've gone past the half equivalence point now. We're going to start off the same way as we have been. We're going to calculate the millimoles of base that we have and subtract that from the acid that we started with. So you'll notice we just have a tiny bit of that propanoic acid left that we have started with, 0.05 millimoles. So at this point, we're going to calculate our new concentrations again with the total volume, and then we'll be using the Henderson-Hasselbalch equation. So we have 2.45 millimoles of the base. Our total volume now is 49.5 milliliters, so 25 plus 24.5. We get our concentration of the base. We're going to take that 0.05 millimoles of the acid, divide by the total volume, and we get our concentration of the acid. We need to calculate the pH, so we're going to use the pKa value that we calculated previously, 4.89, plus the log of the base concentration over the acid concentration. So we get a pH of 6.6 there with sig figs. Our next addition of base is 25 mils of the sodium hydroxide. So with this step, what you'll notice is that we end up with 2.5 millimoles of base, which is equal to the amount of acid that we started with. So if we subtracted the two, we would end up with 0. So what this means is that we have reached the equivalence point on that titration graph. So we have neutralized all of the propanoic acid that we started with. So we're figuring out the pH at the equivalence point. We're going to just look at the equation here for a second. So what's happening here is we have the C3H5O2 minus, and that is going to produce the OH minus and then the HC3H5O2, so that propanoic acid. So this is the reaction that we're looking at. And what we notice here is that we have OH minus, not the H plus. So we would write a Kb expression for this. And at the beginning of the problem, we were working with that propanoic acid, and so we had the Ka value, but we now need the Kb value because we have that hydroxide. So we're going to use our Ka times Kb equals Kw expression to solve for the Kb. So our Kb value comes out to be 7.7 times 10 to the minus 10. And then from there, we can use our ice table. So we can calculate the concentration of the C3H5O2 minus. That's going to be the concentration that we're starting with initially. We're not going to have any of the hydroxide or the propanoic acid to begin with. We would do our change in equilibrium. I'm going to jump down and write the equilibrium expression. So 1-to-1 ratio is there, so we get x squared 0.05 minus x. With the 5% rule, we end up with x equaling 6.2 times 10 to the minus 6. This is going to be the OH minus concentration, so we can calculate the POH from here. Take the negative log of the 6.2 times 10 to the minus 6. That equals 5.21. But then to get our actual pH, which is what we want, we need to take 14 minus the 5.21. So this is a significant shift in the problem now because we have neutralized that acid. So we're now going to be continuing our calculations, looking at that base component and then back calculating our pH from there. So now we know that we've reached that equivalence point, but we're going to continue on with adding additional base. So we can still calculate the millimoles of base that we are adding with 26 mils. So that's going to be 2.6 millimoles. That's going to be what we start with for our subtraction. So we're going to subtract the 2.5 millimoles of the acid that was neutralized. And so the amount of excess base that we have now is 0.1 millimoles. And that again is the sodium hydroxide. So that is a strong base. To calculate the concentration of that, we do 1 mole divided by the total volume. So 51 mils, 26 plus 25. It's the total amount in the flask. We get that concentration. Now again, since sodium hydroxide is a strong base, we can take the negative log of that concentration to calculate the POH. So no need to do an ice table there. That comes out to be 2.71. Then to calculate that pH, we do 14 minus the POH, and that is our final pH for the addition of 26 mils. All right, so this is the last calculation that we're going to take a look at for this problem. So congrats, you're almost there. The addition of 30 mils. So this is significantly past the equivalence point. We're looking at, again, just excess base, sodium hydroxide. Calculate the millimoles with the addition. Subtract off that 2.5 millimoles of acid that we neutralized. We end up with 0.5 millimoles of base. We're going to calculate that new concentration with the total volume. So 30 plus 25 is 55 milliliters. We get that concentration of the excess base. Again, it's a strong base, so we can just plug that into the POH calculation by taking the negative log. The pOH comes out to be 2.04, and therefore our pH turns out to be 11.96. So a very basic pH there. So just to wrap up, we went through 7 different points on this titration curve. So at the very beginning, we have initial calculations that we need to do, working with just the ice table because all we have is the acid. Getting closer to that half equivalence point where the pH equals the pKa, we need to use the Henderson-Hasselbalch equation in these 2 spots. Once we reach that equivalence point, we need to note that we will be working with just the base concentration after that for the excess base calculations. So a lot of things to think about with these. If you have questions after watching this video, make sure you follow up.